Hello everyone, this is the lecture series of Operation Research subject and the course code of the subject is ME405. This is unit number 3rd and lecture number 21, and this is a today topic is branch bound method, and in this method we have discussed about the different types of graphical problem related to the linear programming and sensitivity analysis of this problem, and the some optimal case of this problem. So for my introduction, myself Rahul Kumar, Assistant Professor of Department of Mechanical Engineering, Suresh Gyan, Vihar University, Jaipur. And this is a branch bound method which gives the analysis of different kinds of optimization problem, and it provides one feasible region for the different constraints using here, and it gives the one solution which gives the optimal result of the problem, and this is a very important method for the study of optimum case. And the branch bound method, this is a one type of integer programming method, but in integer programming two types of methods are used. Yesterday class I have in your previous lecture series of lecture I have discussed the cutting plane method, and this is also related to the integer programming, but integer programming gives two types of method. First one is cutting plane method and second is branch bound method, right? So these are some objectives regarding integer programming of method is here, branch bound method. At the end of this chapter, the student able to understand about the concept of integer programming and the determination of integer programming for the organization, and student also understand the concept of branch bound method, and they understand the problem solving techniques. So different types of examples and other type of techniques are used in this example here. So we have understand the problem solving technique for this method. Then this provide the one good example for the organization and for other community by this method. So come to the basic concept of this programming, and if I am talking about the basic concept underlying the branch and bound techniques is to be divide and conquer. It means the branch and bound means first you divide your problem and then combine this problem. So it gives the two things. One is divide and conquer. Since the original large problem is hard to solve directly, and it is divided into smaller and smaller sum problem. So for this method we can divide a large problem into a smaller parts. So, and this problem is converted into the sub problem, and until these problem can be conquered, and the dividing branching is done by parting the entire set of feasible solutions into smaller and smaller subset, right? Means you take a one big problem and this problem converted into a one different small steps, and the conquering is done partially by first is given a bound for the best solution in the subset, and discarding the subset if the bound indicates that it cannot contains an optimal solution. If any problem related to this method and this cannot contain the solution means optimal solution for this case, so this problem is referred to as a discarding the subset, right? So this type of problem indicates that means it have no optimal solution for this problem. So there are basic steps are here. I am using branching, bound and forthcoming are illustrated on the following example, and these following example it will come in this further slides. And the branch bound method. Branch bound, if I am talking about branch bound method, branch bound and the bound method, a solution approach that particulation the feasible solution space into a smaller subset of solution, and the branch bound method gives the one adequate optimal solution, and this is not a solution techniques especially limited to integer programming problem, and this is not a solution technique, this is a problem finding approach, and this approach can be applied to a number of different types of problems. Means one, for this method we can divide the big problem into the small problems, and the branch bound, and if you divide this problem into the different branches, and then these different branches gives the different type of solution for this problem, and the branch bound approach is based on the principle that total set of feasible solution can be pertained into a smaller subset of solution, and these smaller subsets can then be evaluated systematically until the best solution is found. When the branch bound method approach is applied to an integer programming problem, and it is used in conjunction with a normal non-integer solution approach. It is used in conjunction with the normal non-integer solution approach, and we will demonstrate here different type of example. These are related to the branch bound method. For the different examples, just we take one example for this case. Here this is a one example, and this example referred to as a branch bound. So what the maximum function for this case is here? The maximum function for this case is here z equal to 5x1 plus 8x2. This is the maximum function here. Z equal to 5x1 plus 8x2, such that these are the two constraints are used here. First constraint is here x1 plus x2 less than or equal 6, and second constraint is here 5x1 plus 9x2 less than or equal 45. So x1 comma x2 always gives the integer value, and this type of variables, this is always greater than and equal to 0, and it's always integer value, right? And these two constraints are used here for this. So here is x1 plus x2, this is less than or equal 6. So this is the line, this first line shows this line shows the x1 plus x2 equal to 6 line, right? But in the case of second constraint is here 5x1 plus 9x2 less than or equal 45. So this constraint, if I am first put x2 equal to 0 and x1 equal to means x1 equal to 15, right? Something this, and if put here x2 equal to something, then it will give the different value. So the constraints is here, this is the 6 and this constant, this is the 9, x1 equal to 9 and 5 here, and here is x1 equal to 6 and then x2 equal to 6 is here. So this is lies the 6 and 6 here. So these are the two constraints, but these two constraints cut at the point of, these are cut at the point of this red point, suppose like this point. So this is a optimal point for this case. So this is a optimal point for this case. So and the area covered by these two constraints, area covered by these two constraints under this is the optimal feasible area. The solution at that point, this is called optimal solution, and the area under this constraints, this is called the feasible area, right? And then move to the next slide. The next slide gives the utilization of the information about the optimal solution of the linear programming relaxation. So for this here is some fact are given. Some fact are given for this optimal solution. So first fact is for this equation is here, if linear programming relaxation has integral optimal solution, then it gives a x trig value, then x trig is the optimal for the integer programming too, right? So this is a one type of solution which gives the best solution for the integer programming problem solving technique. And in this case, x1 comma x2, just like as a x1 x2, this shows the 2.25 and 3.75. These are the optimal point for the above problem, right? And is the optimal solution of this linear programming relaxation, but unfortunately it is not integral. It is not integral means it is not a unique value. So the optimal solution is 41.25. If you put these values in your function z equal to 5x1 plus 8x2, so it will give a one unique solution for this step. So it is not a integral. The optimal value is here. Optimal value for is here is 41.25. So the fact is here, optimal is here, OPT means this is the optimal value. This is the second fact. LP relaxation, and this is always greater than or equal to the LP integer programming. This is always greater than the LP integer programming for the maximization problem. This is the case only for the maximization of the problem. That is the optimal value of the linear programming relaxation. This relaxation technique only used for the case of case of the branch bound method, and the normal IP shows the integer programming. This is the integer programming, or this refer to the linear programming method, right? So the LP relaxation is an upper bound for the optimal value of the integer program In this case 41.25. In this case 41.25 is an upper bound for the optimal value for the integer programming. So this is the one steps. So we divide into this problem into two sets. First is the branching setup is produced in this slide. So it an attempt to find out more about the location of the integer programming optimal solution and the partition the feasible region of the linear programming relaxation. So for this purpose, choose a variable, any variable, and which gives the fractional value for the optimal solution for linear programming relaxation case. So say x2 here, we choose here x2 value, and observe that as every feasible integer programming point must have either x2 this is less than and equal to 3 or x2 this is a greater than or equal to 4, and this shows the this line shows the x2 value in between 3 and 4 also, x2 value in between the 3 and 4 also. And we keep in mind branch on the variable x2 to create the following two subproblems. Branch of this on the variable x2 to create the following two subproblems. This is the subproblem 1 and subproblem 2 is here. These are the two kinds of problems, subproblem 1 and subproblem 2. So the maximum z equal to 5x1 plus 8x2, and for the max here this these are the two points. First is x2 less than equal to 3 and the x2 greater than equal to 4. So here we take a maximum z function z equal to 5x1 plus 8x2 such that x1 plus x2 less than equal 6 and the 5x1 plus 9x2 less than equal 45, and for this x2 value is here x2 this is the less than equal to 3 here, then x1 and x2 greater than equal 0. For this subproblem 2 this is so the maximum z is equal to 5x1 plus 8x2 such that x1 plus x2 less than equal 6 and 5x1 plus 9x2 less than equal 45, and then x2 equal to x2 is the greater than equal 4. Here is x2 value is greater than equal 4, and this is always must be greater than equal 0, and solve both subproblems. And for this solution, not that the original optimal solution, but we consider here 2.25 and 3.75. These are the recurring solution for this case, right? So move to the next problem, set of problem. So we consider the means we divided into this problem into the two subproblems. So move to the next step. Here just you see in this slide, here the branches are divided into the two sets. Branches are divided into the two subproblems, and first problem is here gives the sum feasible region, and the second problem gives the sum feasible region. So the subproblem 1 for this optimal solution is here 3 comma 3 with value of 39. It gives the value of 39, and the subproblem 2. This is the subproblem 2, and what the optimal solution for this point is here 1.8 comma 4, and it gives the value of 41. So optimal solution for the subproblem 2 point is here 41, and optimal solution for the point subproblem 1 is here 39. So these are the two values, and for these two values we can make a one solution tree. We can make here a one solution tree, and for each subproblem we record the restriction that creates this subproblem, the optimal linear programming solution, and the linear programming optimal value. So for this, so here is all z values, means old values of the optimal point. This is the 2.25 and 3.75, and here is z value is z is equal to 41.25. So this solution is divided into two steps, means x2 is less than or equal to 3 and the x2 is greater than 4 also. So in this two case it gives the value of optimal point. In the first case gives the value of 3,3, and in the second case gives the value of 1.8,4. So the maximum optimal solution for this case is here z equal to 39 and here is z equal to 41. So the optimal solution for subproblem 1 is integral of 3, point. If further branching on the subproblem will yield no useful information, then we can further dismiss the subproblem. In our case, we can furthermore subproblem 1 because of its solution is integral. Because of its solution is integral, and the best integer solution found so far they stored in a incumbent, and the value of the incumbent is denoted by a z star, and the value of the incumbent is denoted by a z star. So for this case, the first incumbent is here 3, this is the z star equal to 39. This is the z star equal to 39, and the z star is a lower bound for the optimal case. Z star for the lower bound for the optimal case, right? And this is the z star equal to 39 here. And in our case, optimal point for the integer programming is 30.39, and the upper bound for this case is here 41. So the problem is here bounded in one interval. So the problem is bounded for which interval is here 3, 4, which gives the boundary for this problem. So we can meet the requirement of this problem. In this case, the next branching setup is here, and further subproblem 1 is divided into the if I am taking x1 variables, and the last case I have taken or I have chosen x2 variable, but in this case I have taken x1 variable. So this is the subproblem 3. New restriction is x1 less than equal 1. For the optimal solution 1, 4,44 with value of 40.55, and the subproblem 4, it gives the new restriction is x1 and greater than equal to 2, and the subproblem is infeasible region. This is the subproblem in the infeasible region. So draw this problem, these 2 points. So this is the subproblem 3 and this is the subproblem 4 is here. So here the different kinds of optimal point is given here. So this is the one optimal point is here. This red sign shows the optimal point, right? So here the value is 1, 4,44. It will give the maximum function value z is equal to 40.55. It will give the maximum function value z equal to 40.55. So for this case, it reduces the value, right? So it verify this statement, means linear programming problem. Optimal solution of you find from the linear programming. This always greater than the problem of integer programming solution, right? So for the integer programming solution is here 40.55, and the integer programming solution is 40.55, and the linear programming solution is 41 point something, right? And the solution, this is the solution is 41.25, and so this gives the least solution 40.55. So the branches are again divided, but in this case of surplus 3, right? In this case of surplus 3, it gives the infeasible region. It gives the infeasible region for this case. So move to the next. Okay, then this is the continuation of the solution tree. So the solution is already again is subdivided into the, suppose this solution gives the integer value. This is the 39, but here some fractional value is present. So this is divided into two types. So in the S3, this is a subset of S3, and which is x1 less than and equal to 1 is here, which gives the value of 1, 4, 4, 4. So the feasible solution is here z equal to 40 minus 5, 40.55. So but in this case, S4 case, this is the outside the feasible range. So this is the this gives the infeasible solution. If the sub problem is infeasible, then it is further in the fat term. In our case, sub problem 4 is infeasible or infinite. So the upper bound for the optimal solution, if I am consider here integer programming, is updated 39, less than equal to optimal solution integer problem and less than equal to 40.55. So the here is problem is varied in the range of 39 to 40.55. This is the one range of this problem. And the next branch sub problem 3 on x2, then note that the branching variable might recur, right? So this is the different branch solution, and this is the main solution, and it is subdivided into the two steps, and this gives the integer solution, and then this is a not integer solution. So it will again divide into two steps. So here is this S4 gives the infeasible solution, and this S3 gives the one non-integer solution for this case. Then move. So the branch subproblem 3 on x2, this gives the subproblem 5 and subproblem 6. For this case, here it will give a two types of optimal point. One is 0, 5 and another one is 1, 5. 1, 4 is here. So the subproblem 5, this gives a new restrictions, and this is a x2 less than equal 4, and the feasible region in the segment joining as a 0, 4. Suppose this 0, 4 and 1, 4. So for this case, the optimal solution, it will give a value of 37. This is the least solution of this problem. So but in the case of subproblem 4, now restriction is here x2 greater than equal 5. X2 is greater than equal 5. So for this case, this is this line here. So this is this problem, right? This problem means this point, and this gives the value of 0, 5, and again it gives the feasible optimal solution for that this point here is 40. This is a 40. So move to the next step. And here, just you see here, this problem is again subdivided into the two groups. So this is suppose and continue from this side. Here this S4 gives the infeasible solution. So we will stop here, and this and then S3, this will gives the 40.55. This is the non-integer solution. So this here, this will always divide into two groups, and first group is x2, this is less than equal to 4, and x2, this is the greater than equal to 5. So it gives the solution of 37, 40, right? 37 and 40. If the optimal value of a problem subproblem is less than or equal to z star, then it furthermore made just like in our case subproblem 5 is the further made because 37 less than or equal 39 equal to z strict. In the subproblem has integral optimal solution x strict and its value greater than z star, and then x star replaces the current incubant. In this case, subproblem 5 has integral optimal solution. Subproblem 5 has integral optimal solution and its value 40 greater than 39. This will give the z star value. Thus 0, 5 is the new incubant and new z star equal to 40. This is the solution of this problem. And if there are no unfurther made subproblem left, then the current incubant is an optimal solution for integer programming. In our case, 0.5 is an optimal point solution with optimal value of 40. So this is the correct answer for this case. This is the correct answer. 40 is the correct answer. So in the last case, here both are integer values. Both cases given the integer values. So further subdivision of the problem is not possible here, and you will stop only this step. So this is the one way to finding the solution with the help of branch and bound method. So the result for this case is here 40, right? This is the second problem of branch and bound example, and you can solve this problem in your branch integer programming with branch and bound method. Here the maximum function is here z equal to 8x1 plus 11x2. This is such that 5x1 plus 7x2 less than or equal 14. These are the two types of constraints. And another constraint is 0 always greater than less than or equal x1 and x2 always less than equal to 1 integer. So this is the one problem, and just note down this problem and you will solve in your just like as a homework, right? So we move to the next problem. So here I will give some introduction regarding linear programming model. If I am talking about the linear programming, so this is a objective function. This is the objective function, and in that case, we can say that previous case, this is the maximization case, but any problem related to the minimization case. So what you will do here? What you will do here? So this is the problem. For this, so here minimum function is here c1x1 plus c2x2 plus cn xn, and this is the objective function, and these are the two constraints, and these are the two constraints are a11 x1 a12 x2 plus dot 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 plus a1n xn less than equal to b1, and the second case a21 x1 plus 22 x2 plus dot dot plus a2n xn less than equal b2. So this is the second type of constraints, and am1 x1 plus am2 x2 plus dot 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 plus amn xn less than equal to bm. This is the if xj greater than equal 0 and the j belongs to 1, 2, 3 like that up to n, and this is the variable restriction. And in the case of matrix form, this is a minimum ctx ax less than equal b and x greater than equal 0, where x comma c shows the n vector and A shows the M comma N matrix and B is the M vector for this case. So this is the one linear programming model for the minimum case. But if I am consider the maximum case for this LP example is here. This is the maximum case problem, x1 and x2. This is subjected to 2x1 plus x2 less than equal 4 and the 3x1 plus 4x2 less than equal 12, and the xj greater than equal 0 and j is goes to the 1 comma 2 comma 3, and the maximum 1 comma 1, this is the transpose of x1 x2. This is subjected to just like the means here this problem is converted into the matrix problem. So here you can write 2 1 3 4 x1 x2 4 less than equal to 4 by 12. So the here is x1 x2 greater than equal 0 comma 0. So this is the main problem related to one set of this problem. We can draw this problem with the help of maximum x1 plus x2 subjected to 2x1 plus x2 less than equal 4 and 3x1 plus 4x2 less than equal 12. So we draw two constraints here. This is the solution space, or this is the feasible region of this problem. So here is two kinds of constraints, and this will cut at the point of this. So first you see here, this is a one point, and if this function gives the integer value, so the furthermore division of the problem is not required. If this optimal point gives the non-integer value, then we give the two cases, means upper bound and the lower bound of the problem, and find the new optimal point for this case. And then again you find the two optimal point gives the again some function value, means maximum z function value, and this function value is in the form of integer. If this is not integer, then you again further divided this step. So this is the branch and bound method for this case. So here this problem gives the 0.8 and 2.4. So it will give a non-integer solution. So this problem is again divided into the two steps. This is the x1 less than or equal 0 and the x1 greater than or equal 1 here. So it will give the two functions 0 comma 3 and 1 comma 2 is here. So x1 x2 it will give say one integer value. For this case here x2 is again divided, and this gives the objective function 3, x1 equal to 1 and x2 equal to 2. For this x1, if I am divided this here, x2 is here, right? So it will give the x1 equal 0 comma 3. So it gives the one integer value, right? So again subdivision of the problem is not possible. So this is the one-way solution of the branch and bound example here. So we move to the next section of this problem. This is the objective question problem for your lecture series. For this case here is this is a one function which determine the rank of this job, right, by using this formula. So this is a MCQ problem section. For this section, and the first question here is branch and bound is a miss. We find the correct answer of this problem. So this is a problem is A option is here, problem solving technique. B option, data structure. C is sorting algorithm, and D is type of tree. So you give the correct answer for this question, and just you wait for 5 seconds. So the correct answer, just you find the correct answer, and the correct answer for this question is here, branch and bound is a problem solving technique. Branch and bound is a problem solving technique. So the correct answer is here, A is the correct answer. And then move to the next question. For this next question, which of the following is not a branch and bound strategy? Which of the following is not a branch and bound strategy to generate branches? And this is the LIFO branch and bound, FIFO branch and bound, and lowest cost branch and bound, and highest cost branch and bound. And what is the correct answer of this question? Just you think about this question and find the, here is 4 option is given. So the correct answer of this problem is highest cost branch and bound. Highest cost branch and bound. So this is the correct answer of this problem is here, right? So D is the correct answer for this problem. Move to the next problem. And which data structure is used for implementing a LIFO branch and bound strategy? Implementing the LIFO branch and bound strategy. So first one is stack, queue, array, linked list. Stack, queue, array, and linked list. So here is stack. Stack is the right answer for this question. Which gives the data structure is used for the implementing a LIFO branch and bound strategy. So move to the next question. And in this question we give the which data structure is used for implementing a FIFO. FIFO means first in first out branch and bound strategy. This is stack, second B option is queue, C is array, and D is linked list. So the correct answer is here Q. Q is the FIFO, implementing a FIFO branch and bound strategy. So we move to the next slide. Which data structure is most suitable for implementing best first branch and bound strategy? This is the stack. Here is 4 option is given. First one is here stack, queue, priority queue, linked list. So the correct answer for is here is Q is the correct answer. So B is right answer for this question. And then move to the next 6th question. In this 6th question, which of the following branch and bound strategy leads to breadth first search? So this is the 4 option is given here. 4 option is LIFO branch and bound, B is the FIFO branch and bound, C is the lowest cost branch bound, D is the highest cost branch bound. So the correct answer of this question is here FIFO branch and bound. 6. B is the right answer for this 6th question. Then move to the question number 7. Which of the following branch and bound strategy leads to depth first search? This is for the A option is a LIFO branch and bound, FIFO branch and bound, lowest cost branch and bound, and the highest cost branch and bound. So A is the correct answer. LIFO branch and bound method is used to give the leads to the depth first search, right? Choose the correct statement from the following. Branch and bound is the more efficient in backtracking. Branch and bound is not suitable where a greedy algorithm is not applicable. Branch and bound divides a problem into at least 2 new restricted subproblem, and backtracking divides a problem into at least 2 new restricted subproblem. So the correct answer for this problem is here C is the correct answer. And then move to the next question. So this is the 9 MCQ problem. And which of the following can traverse the state space? Tree only for DFS manner. So the correct answer for this problem is here D. D is the backtracking. This is the right answer for this question, but 4 option is given here: branch and bound, dynamic programming, the greedy algorithm, and the backtracking. So the D option is the backtracking. This is the right answer for this question. Which of the following are the advantages of decision tree? A is possible scenarios can be added. Use a white box model if given result is provided by a model. And worst best expected value can be determined for the different scenarios. All of the above mentioned. So the correct answer of this problem is here, all of the above mentioned. So move to the references of this lecture. So these are the different kind of references we have taken here for this lecture. So this is last of this lecture. So thank you for this class and giving me a very valuable time. Thank you all of you. Thank you.